Okay, so today we're going to be talking about substitution. And this is, well, actually, the first thing I want to do is talk about the last problem that was in the exam. And I just want to use this as a quick example of how we can use variation of parameters to solve problems like this. Okay, so this problem number 10 on the exam, it was so this was xy prime is equal to x e to the minus y over x plus y. And so some people had noted that we hadn't talked about anything in class that would allow you to solve a problem like this, which is both true and not true. So you could solve this one using variation of parameters. It just wasn't, we had only used variation of parameters to solve linear problems. And this is definitely not a linear problem. So variation of parameters actually will work for this as well. And so I'm going to just walk through how to do that. So if we put it into the form that we're used to for using variation of parameters, we get xy prime minus y is equal to x e to the y minus y over x. And then if we divide through by x, we get y prime minus 1 over x y equal to e to the minus y over x. And so our sort of homogeneous version of this is y star prime minus 1 over x y star is equal to 0. And of course, we know that this is now a linear equation. And so y prime is equal to e to the minus integral of p of x. And so in this case, p of x is minus 1 over x dx. And of course, those minuses cancel out, and we're just left with e to the natural log of x plus some constant of integration. So this is just x. And what we're looking for with variation of parameters is a solution of the form, let me write it like this, y of x equal to u of x y star of x. Okay. So if we plug this back into our equation right here, well, y prime, we need to figure out what that is. That's u prime y star plus u y star prime, and we can figure out what this is. U prime x plus u. Right. And y is just, of course, u x. So if we plug this back into this equation right here, what we get is u prime x plus u minus 1 over x times y. So that's just minus u equals e to the minus y over x. That's just e to the minus u. This part cancels out. And what we get is u prime x equals e to the minus u. And this is actually a separable equation. So what we have is du dx is equal to e to the minus u times 1 over x. And so we get e to the u multiplying e to the u to the other side. And then multiplying dx to the other side, we get dx over x. Let's move over here. And what we get from this, of course, e to the u on the left-hand side and natural log of x plus some constant of integration, right? And then solving for u, we get u is equal to natural log of the natural log of x plus c. And there's our solution. Well, that's our solution. That's u. Now we need to just get y, and so that's x times the natural log of x plus c. And we have our solution. So this was just an example of variation of parameter. This illustrates a very important principle in doing math, and that is when you don't know what to do, just try something reasonable and see if it works. Now, this is not to be confused with the very common technique that students will use, which is when you don't know what to do, write something that's similar to something that you know, but it's nonsensical and hope I don't notice. Now, some people did this to me, but we always notice. Okay. So this is one way of doing it. This worked out pretty nicely. But there's another technique, the technique we're going to talk about today, which we can actually use to solve this type of problem, and it's called substitution. And since I did see some people use this method on the exam, I can only assume they either read ahead in the readings and got to this early, or they cheated and used a symbol app or something. So substitution, how does this work? Roughly speaking, let's say this is the rough idea. We replace the complicated part of an ODE with a new variable, rewrite the equation, and hope for the best. This is another example of that. Try something reasonable and see if it works principle. You'll remember use substitution from back in the day. This is a very similar idea to this. So in use substitution, oftentimes we didn't know ahead of time what a good substitution was. We could kind of guess based on the form of the equation, and a lot of times, those guesses turned out to be right because we were working on problems where the person who wrote the problem knew how we were going to guess and gave us an easy way out. But it's sort of the basic. It's the sort of the same basic idea. So we replace with a new. I should say this is the new dependent variable, and oftentimes we use just like we did in use substitution. So using this same example, so we had x y prime is equal to x e to the minus y over x plus y. y over x looks complicated. So we're going to make the substitution u is equal to y over x. In fact, if we divide through by x to get this y prime by itself, we get y prime is equal to e to the minus y over x plus y over x. And now we see on the right-hand side, we have a function entirely in terms of y over x. So we have this y prime on the left-hand side and f of y over x on the right-hand side. And this is through an unfortunate mistake of history where we end up using the same word for two mostly unrelated things. These are also called homogeneous. Unfortunate mistake of history, but we're stuck with it. So let's just try to make the best of it. So in fact, these types of equations, these types of ODEs are always solvable. We can always find a solution, at least implicitly. We can always find an implicit solution to one of these. And why is that? Because if we go back and look at our choice of substitution here, then we can rewrite this as y is equal to ux, and taking the derivative on both sides, we get y prime is equal to u prime x plus u x prime, which is just 1. Okay. So then this equation right here can be rewritten as u prime x plus u on the left-hand side and f of u on the right-hand side. And just a little bit of rearranging, we get u prime x equals f of u minus u. Notice all of this is still just a function of u, just a function of our dependent variable. And then dividing through by x, we get u prime is equal to f of u minus u over x. And this is separable. So we can do the separation of variables. We get on the left-hand side d of u over f of u minus u on the left-hand side in terms of the dependent variable. And on the right-hand side, we get, d of x, dx over x on the right-hand side. And so at the very least, we have an implicit solution. If we can do these integrals, then we can get an explicit solution. Well, if we can do these integrals, then solve for u, and then we can use u to get y. So let's try to write out the steps that we would go from here. So integrate, solve for u, and then ultimately solve for y. Now, this step right here is easy. After we've solved for u, it's easy to solve for y because we already know what y is in terms of u. Typically, when we make these substitutions, we make them so that it's easy to go back to writing things in terms of y. So really, once we get to the point where we've solved for u, we'll consider it we're pretty much done. It's just a matter of rewriting it in terms of y. That's the easy part. Okay, so returning to our example, what did we have? We had, let me rewrite it. Y prime was equal to, I'm sorry, y prime, yeah, now let's write it like that. Y prime is equal to x to the minus y over x plus y over x. I believe that's what we got up here. Sorry, e to the minus y over x, not x. So that's right here. So rewriting this in terms of u, we get on the left-hand side u prime x plus u, and on the right-hand side e to the minus u plus y over x, which is just u. So we can cancel out the u's on both sides, and we're left with u prime x equals e to the minus u. And we can, of course, rewrite this as the integral of e to the u du equals the integral of dx over x. And we know how the rest of that goes. It's just now we're at the same point that we last. The last time we worked through this same problem using variation of parameters. So this is an illustration of another principle of math, which is there's always more than one way to solve a problem, and you should know as many as you possibly can. Okay. See how we're doing on time. That's 18 minutes. So let's move on to another example of substitution. So we can also use substitution to solve Bernoulli equations. And remember, these were equations of the form y prime plus p of xy is equal to q of x, y to the r, where r is not 0 or 1. So if r was 0 or 1, this would just be a linear equation, and we already know how to solve those. So we're going to assume that it's not 0 or 1. This detail will actually come up again soon. Okay. So this time we need to make a fairly clever choice for our substitution. So if we divide it through by this y to the r, then what we would get is y to the minus ry prime plus p of x y to the 1 minus r equals q of x. And it looks like we're pretty close to a linear equation. The only problem is that instead of a y here, we have a y to the 1 minus r. So we're going to make that as our substitution. So u is equal to y to the 1 minus r. And if we take our derivative, what we get is u prime is equal to taking the derivative on the other side, the chain rule and everything. So the exponent comes down, we get y to 1 less than 1 minus r, that's just minus r. And multiplied by the derivative of what's on the inside, what was on the inside was y. Excuse me. What was on the inside was y, and so its derivative is y prime. And lo and behold, what we end up with right here is just the thing right here. And so things are working out pretty nicely. So if we now make our substitution, then we can substitute, well, let's rewrite this. This is 1 over 1 minus r times u prime is equal to y to the minus r y prime. So we can replace this first term with 1 over 1 minus r times u prime. The second term we can replace with minus e of x u, and q of x can just stay q of x. And now if we multiply through by 1 over r, what we're left with is y prime minus 1 minus r e of x u equals 1 minus r times q of x. And this is linear. And so what we've ended up with is a linear equation, which we know how to solve. A linear first order equation. This is our new p of x. This is our new q of x. And once we get to the end, well, we need to figure out how to solve for y in terms of u. We can just sort of invert this equation right here. Raising both sides to the power of 1 over 1 minus r, we get u to the 1 over 1 r equal to y. And this would be how we would solve for our original, in terms of our original dependent variable. Okay, I'm going to move on now to another type of substitution. Does anybody have any questions before I do move on? I think I'm going to wait until after this next substitution before I start working some examples of each of these. So let's go ahead and do this other substitution. So this first one was for what we think of as homogeneous equations. We also had a substitution that would work for Bernoulli equations. Of course, we already had a way of solving Bernoulli equations before, and that was variation of parameters. Okay, so now there's another type of equation. I don't know that this one has a special name. I'll switch to another color. This one is equations of the form y prime is equal to f of ax plus by plus c. So if we can take our original right-hand side and rewrite it in terms of this right here, ax plus by plus c. Okay. So this is the substitution that we'll make. We'll make substitution u is equal to ax plus by plus c. And again, we'll figure out what u prime is. So u prime is going to be equal to, let's see, the derivative of ax with respect to x is just a. The derivative of by with respect to x is by prime. And the derivative of c is just 0. So now we can rewrite y prime in terms of u. So we get, let's see, y prime is equal to 1 over b times u prime, okay? And so what we get is 1 over b u prime minus a for the left-hand side. And for the right-hand side, we just get f of u. And of course, this is separable because what we get is u prime on the left-hand side after doing a little, moving everything else over to the other side, b times f of u plus a. And so this is a function entirely of u. And so, of course, we do just the same thing that we normally do. We can rewrite like this, and we get the integral of dx is equal to the integral of du over g of u, which I'll just write out as b f of u plus a. And at this point, we have an implicit solution. Now, if we can, of course, decide it's just x plus constant of integration. This side, we need to know if we can find an antiderivative of this or not. If we can't, then we can just say that it's an explicit or an implicit solution. There's a solution implied by this equation, but we don't know exactly what it is. So finally, the book gives us this nice table of some clever choices of substitutions. I'll title this Clever Substitution. Substitutions that may not be immediately clear to you whenever you see an equation. So they say when you see on the one side and try substituting on the other side. So what are their suggestions? When we see y prime, try u is equal to y squared. When you see y squared y, try u is equal to y cubed. Of course, they give these without justification, and I will do the same. If you see cosine y prime, try sine y. You see sine y prime, try cosine y. You get kind of a feeling for the pattern. If you take the derivative of the substitution, you get this thing on the right side. And finally, if you see y, ooh, how did that happen? If you see y prime e to the y, try substituting for e to the y. Okay. All right, now let's try some examples. And I'm going to go to the book for these. So let's make a little space. And we'll try, let's try this one. So y prime equals x plus y plus 1 squared, and y of 0 is equal to 0. I'll give you a minute to try. Is there anybody who wants more time to try this out? Okay. All right. Well, let's see what I come up with. So I'm going to make the substitution. U is equal to x plus y plus 1. So I get that u prime is equal to 1 plus y prime. And so what I'll get for this is u prime is equal to, well, let me just write it out. Y prime is equal to 1. Y prime is equal to u prime minus 1. I'm a little out of it today. And so we'll make the substitution u prime minus 1 is equal to u squared, or u prime is equal to u squared plus 1. And so what I get for this is that on the one side I have du over u squared plus 1, and on the other side I have dx. I'll integrate both sides. Okay. So on the left-hand side, I get the famous integral for that gives us arctangent of u, sometimes written as tangent inverse, but as you'll remember, it's not really an inverse. And on the right-hand side, we get x plus some constant of integration. And of course, with the arctangent, I can take the tangent of that and end up with what I started off with. If I take the tangent of both sides, just get u on this side, and I get tangent of x plus c on the other side. Okay. And maybe it was easier. Let me stop right here and go back to stuff. Oh, actually, I want to say if you take the tangent of the arctangent, you always get back what you started with. But if you take the arctangent of the tangent, that's not always true, right? That's why they're not complete inverses of each other. So just one-sided inverses. Now, on this step right here, it might be easier to figure out what our C is based on the initial condition, because we can plug in a 0 for x and a 0 for u, and the arctangent of 0, as you probably know, is 0. And so, or did I get that right? I'm messing this up. Oh, I know why. Because u is not 0, y is 0. And so when we plug in 0 for x and 0 for y into this right here, we get that u is 1. That seems much better. And so the arctangent of 1, the angle that we could put into the angle between minus pi over 2 and pi over 2, that we can plug into tangent to get 1 is pi over 4. And on this side, we get c. So we get c is equal to pi over 4. And we can rewrite this now as u equals tangent of x plus pi over 4. And then finally, we want to go back to writing things in terms of y. So y is equal to u minus x minus 1. And so y equals tangent of x plus pi over 4 plus or minus x. Let me return to the book for an example. The example, actually, yeah, this is the example from the exam. I shouldn't have said that out loud. Okay, let's try one from the other book. Switch to another color. Y prime plus y times x squared plus 1 plus x y to the 6th equals 0. So this is a Bernoulli equation. Feel free to solve this either way. You can either use the variation of parameters or you can use the substitution. Yeah. Give this a shot and we'll come back to it in just Anybody want more time to look at this one? Okay. So for this one, we have, well, we can go back to looking at this in terms of a Bernoulli equation, or the terms that we were looking at it through before. So in that case, p of x, we would have p of x is x squared plus 1. Q of x is negative x, and r is 6. So let's try with the substitution method. So the substitution we decided we wanted to do for a Bernoulli equation was u equals y to the 1 minus r. So in this case, that will be y to the minus 5th. So what does that give us? That gives us u prime is equal to minus 5 y to the minus 6 y prime. And so we have y prime is equal to u prime y to the 6th. Let me do that. Negative 1/5 in front. So this first term we'll rewrite as minus 1/5 u prime y to the 6th. Okay. Let's see, this y we will rewrite. No, I think this is going to be easier if I just do the rewriting like I did before. I think this is sort of the method that they go through in the book, but I think the way that I do it is actually easier. So let's go back to this step, and I'm going to divide through by y to the 6th. So I get y to the minus 6 y prime plus y to the minus 5th x squared plus 1 plus x equals 0. I think this is easier. So y to the minus 6th y prime is just u prime. Well, I do have to rewrite this part. So we'll get negative 1/5 u prime equal to y to the minus 6th y prime. So this will be minus 1/5 u prime. And then y to the minus 5th is just equal to u. So this is x squared plus 1 u. And then just plus x equals 0. Okay. So let's see, I'll multiply through by 5, and I'll move that x over the other side, just so it's in the form that we're used to. We get this. And now our new p, which I'll call p hat. This will be 5 x squared plus 1, and our new q hat will be equal to minus x. And so if we use, what do we want to use? Let's use integrating factors. So our integrating factor will be, we called it r of x. Now we're running into using the same letters now. Let's use s of x. Avoid collision. So this is e to the integral of our new p of x. And so what will that be? So this will be e to the, let's see, 5/3 x cubed plus 5x. Yep. The integral of this thing, e to the integral of that thing. And so if we multiply through by that, we get e to the, I'm just going to write this as e to the capital P, or a capital P of x, is an anti this thing. So 5/3 x cubed plus 5x, just so it's easier to write. So this is e to the capital P u prime plus e to the capital P prime u is equal to e to capital P. And I don't want to forget the negative sign. So this side, of course, we can rewrite as e to the capital P u prime equals minus e capital x. And are we in trouble here? Hopefully not. So what we're going to get is e to the capital P u is equal to the integral of minus the capital P x dx. Hopefully everything's still okay. And let's see, can we figure out what this integral is? So this should be integral, we'll move the minus, e to the 5/3 x cubed plus 5x x dx. Which did we solve using integration by parts? I believe so. Because if we take 5/3 x cubed plus 5x, this is equal to x times 5/3. Be a little careful. So what I want is the integral of e to the capital P of x times little p of x dx. That would be easy to integrate. Unfortunately, we don't have that. We have e to the little p of x was 5x squared plus 5. This would have been a lot easier. And change the original problem so that it's easier to solve. Let's just leave it like this. Let's just stop here. So we'll just write this as u is equal to e to the minus capital P integral of negative p to the p of x, the capital P x dx. And just not worry about the calc 2 part where we figure out what the integral thing is. Yeah. Yeah, I think I'm content to leave it like that. Did I write the problem down wrong? Or maybe someone can tell me that I'm just missing a really obvious detail. But this doesn't seem like exactly, this is not exactly an easy thing to integrate, at least as far as I can tell. Because if we were doing integration by parts, we could take the derivative of this and the integral of this. But in order to take the integral of this, we need the derivative of the exponent to be sitting around, right? This is what I get for not trying these problems out before class. So, lesson learned. Okay, let's just move on to the next one. Actually, it's 11:20, so I'll stop there.